So coming to today's lecture session. So today's lecture session is about combustion in SI engine, right? And the outline of the presentation is like this. Let us start with the recap of 4-stroke petrol engine, and we will get into the combustion in SI engines under ideal condition. Theoretically, how do we have the combustion process in SI engine? That we will start, and then we will go to the actual stages of combustion. Combustion in SI engine under actual condition. Then finally, we will be discussing about some of the terminologies related to the combustion in IC engine. Okay, so this is what we are going to discuss today. Coming to the working of 4-stroke petrol engine, right? So we made a table like this, right? When we are discussing about working of 4-stroke petrol engine, what is the first stroke? Whether it is petrol engine or diesel engine, in a 4-stroke engine, what is the first stroke?
Suction.
Yeah, suction stroke or intake stroke. So where during the suction stroke, inlet valve will be open, exhaust valve will be closed, and the piston will be moving from, during suction stroke from TDC to BDC, and the crank angle turned will be from 0 to 180 degree. Okay. Now this is revolution 1. So this is now revolution 1 starts. Okay. And what is the next stroke? Next stroke is compression stroke, during which both the valves will be shut. Inlet valve as well as exhaust valve, both the valves will be shut, and the piston will move from BDC to TDC. So the charge air fuel mixture that is present inside the combustion chamber, or which is present inside the engine cylinder, that is subjected to compression, right? Piston moves from BDC to TDC, so volume of the engine cylinder is going to decrease. So whatever air fuel mixture that is present inside, that is going to get compressed. So pressure increases, temperature also increases. So at the end of the second stroke, that is compression stroke, the crank angle turned is going to be 180 to 360 degrees. So when 360 degree is completed, that means revolution 1 is complete. First revolution of the crankshaft is complete. Okay. Still we have 2 more strokes for the complete cycle of operation. To complete the cycle, still 2 more strokes are there. What is the third stroke? Expansion stroke or power stroke, right? So during this stroke, which valve is open? Yes, during the expansion stroke, which valve will be open? None of the valve will be open. Both the valves are shut. Okay. And what about the movement of the piston? Piston will move from TDC to BDC. Before that, spark has to be introduced. For ignition, the spark has to be introduced. Only then the ignition starts and combustion takes place. Okay. And the piston will move from piston moves from, yes, TDC to BDC. What about the crank angle? Hello? Yes?
Second revolution, sir.
Yeah, second revolution starts. So next 120 degree of revolution is going to start. That is from, if you are going to start from 0, from the first revolution, if you are going to consider, now then this is going to be 360 to 540. For the second revolution, it is 0 degree to 180 degree. Because normally we will consider the crank angle as 0 degree whenever the piston is at TDC, right? So here I have highlighted 2 things here in the expansion stroke. One is the TDC, right? So we'll, sometimes what will happen, we will start measuring only from TDC. If that is the case, then they may say like from the angle turned will be after TDC these many degrees, before TDC these many degrees. So for second revolution, they may represent, some of the authors, if you refer in the books, some of the authors, they will refer like from 0 degree C. For the third stroke, that is for the expansion stroke. That means they are considering TDC as 0 degree. Crank angle is 0 degree for TDC. So after that, the movement of the piston beyond TDC, that is while moving from TDC to BDC, that angle can be represented like this also. If you are going to start from the beginning, including revolution 1, then it is 360 to 540. If it is for the revolution 2 alone, if you are going to consider, then the angle turned during the expansion stroke is from 0 to 180 degree. Okay. So remember, during the stroke only, this spark is going to be introduced. Remember, this lecture is about combustion in IC engines, especially SI engine. So for combustion, if you are going to study, then the beginning of the combustion starts as soon as the spark is introduced in the engine cylinder, right? As soon as the spark is introduced, then ignition starts. So this is important, and TDC is important because from there only we are going to consider the movement of the piston. So where the crank angle is 0 in the revolution 2. And the last stroke is exhaust stroke. Which valve will be open during exhaust stroke? Exhaust valve will be open, whereas the inlet valve will be closed. Correct. And the piston will be moving from BDC to TDC. As the piston moves from BDC to TDC, the products of combustion are going to be sent out of the engine cylinder, right? So during this time, as a whole, if you are going to consider, then the angle turned by the crank is 540 to 720, whereas if you are going to consider for the second revolution alone, then it is 180 to 360. So this is second revolution completion. Okay. So when we are going to discuss for the combustion in the IC engine, so these two strokes, compression stroke and expansion stroke, we are going to consider. So this is what we are going to discuss in detail. Okay. So these two, compression stroke and expansion stroke. So coming to the combustion in SI engine, let us start with the ideal condition, right? Listen carefully, or step by step I am going to discuss, right? This is for ideal condition, not the actual condition. Theoretically we are going to discuss. So now I have told you that we are going to concentrate only with the two strokes, compression stroke and expansion stroke. For analyzing the combustion in the engine, in the IC engine, we are going to consider mainly the compression stroke and the expansion stroke. These two strokes we are going to consider. So now, where is the piston located now in this diagram? Where is the piston located? Piston is at the BDC. Now compression is going to start. For compression stroke, piston will move from BDC to TDC. Okay. So this is the beginning of compression where the piston is at the BDC, and I am going to draw a engine cylinder pressure versus crank angle turned. Right. This we call it as P theta diagram. P is the engine cylinder pressure, theta is the crank angle turn. So we are going to represent this compression and expansion process alone in a P theta diagram, pressure crank angle diagram, right? Engine cylinder pressure versus crank angle turned. So that we are going to draw to represent these compression beginning, ending, then your ignition process, combustion ending, everything we are going to represent in the P theta diagram. So this is the very first state I am going to represent in the P theta diagram. So that I am going to represent using point A. In the P theta diagram, I am going to represent this state, the beginning of the compression. This state I am going to represent by point A. Now, what is the after the compression has to be completed, right? So when the piston moves from BDC to TDC, so it is going to reach, this is the TDC position. So this is end of compression, right? So compression stroke is completed and the angle turned is going to be 180 degree, right? Half of the crank revolution, 180 degree angle has been turned. So this is end of compression. This state of the air fuel mixture that is present inside the combustion chamber, that is represented by point B. Okay. So what has to happen now? Once the piston reaches the TDC, now combustion has to take place. Whatever the air fuel mixture that is present there, that is present only in the clearance volume. The gap between your TDC to this, your cylinder head. So that gap is very minimum. That is the minimum volume that is available. In that minimum volume, the air fuel mixture is present now, which has to undergo combustion. How the combustion will occur? We have to introduce spark. So this is the spark plug, centrally located spark plug. So at the end of the compression stroke, when the piston reaches the TDC, spark plug ignites. Okay. Spark is introduced. Okay. Piston is at TDC, spark is introduced now. Right. So the air fuel mixture, it will ignite. So this state is indicated by point C. The moment you are going to introduce the spark, that is given by point C. So now what is going to happen? Air is there, fuel is there, and heat is also there. So combustion takes place. So once the combustion takes place, then huge amount of heat is going to be released. During the combustion process is an exothermic reaction. So lot of heat is going to be released. And remember, piston is at the TDC, volume available is less. What will happen to the pressure? The combustion is taking place, then the products of combustion has to expand because more amount of heat is being released. The volume is minimum here. So the pressure is going to be very high. So when the combustion takes place, we will have a sudden surge in pressure, sudden spike in pressure is going to be there. Because of the sudden rise in pressure, that products of combustion with a high pressure, that is going to move the piston down. So piston moves down from TDC to BDC. This is what we call it as the expansion stroke or the power stroke. Okay. So this point, the end of the expansion stroke, piston reaches the BDC, right? This is your end of the expansion stroke. So that we are going to represent by point D. So in the theoretical P theta diagram, this is a theoretical condition. Under ideal case we are discussing. There are 4 points: point A, point B, point C, point D. Point A is nothing but the beginning of compression. Point B is the end of compression. Point C is the moment the spark is introduced in the combustion chamber. Point D is the end of the expansion process, right? So all these 4 we are going to represent in the P theta diagram, right? So this is the P theta diagram under ideal condition. Okay, so this is the P theta diagram for the ideal condition. The x-axis is the crank angle turn. X-axis is the crank angle turn. This y-axis is the engine cylinder pressure, right? The cylinder pressure is given in the y-axis, whereas in the x-axis we are having the crank angle turn. So what is point A? Point A is the beginning of compression, right? So here I have represented this is second stroke in a 4-stroke engine. Second stroke is the compression stroke, where the angle turned is 180 to 360. Correct. So the angle turned during the compression stroke is 180 to 360. The beginning of compression is given by point A. So now as the piston moves from BDC to TDC, the pressure inside the engine cylinder is increasing. And once the piston reaches TDC, where the minimum volume is there, only clearance volume is available for the air fuel mixture. So that is represented by state point B. So that state is represented by point B, right? So this is the end of compression. Now spark is introduced. When the spark is introduced, ignition starts, right? So the spark introduction, the ignition starts, the pressure is going to be higher. So that is represented by point C. Remember, piston has not started to move. Piston is still in the TDC. It has not started to move, but there is sudden rise in pressure, sudden surge in pressure, right? So that is represented by point C. So because of the sudden rise in pressure, the products of combustion that is going to exert pressure on the piston, and the piston is going to move down from TDC to BDC. Piston is going to move down. So this we are going to call it as expansion stroke. So this is compression stroke. This is the ignition. Spark is introduced, sudden rise in pressure. Because of sudden rise in pressure, the products of combustion is going to pull down the piston. So piston is going to move down from TDC to BDC. So during that stroke, another 180 revolutions is going to be completed. So this is given as 362 plus 180 is 540 degree. This is the crank angle turn. So this diagram we call it as P theta diagram. P theta diagram for the theoretical condition of combustion in the SI engine. In reality, it won't be like this. Okay. So this was studied in detail. Now let us come to the actual condition when the combustion takes place in the SI engine, right? So this was initially studied by a person named Ricardo, right? Sir Ricardo. He was considered as the father of engine research, right? He did a lot of research in the combustion, and he was considered as the father of engine research. Okay. So what he did, this combustion process that takes place inside the engine cylinder, he had divided into 3 stages or 3 phases, right? Phase 1, phase 2, phase 3, or stage 1, stage 2, stage 3. So the combustion process that takes place inside the engine cylinder was divided into 3 stages, right? This was done by Sir Ricardo. So the first stage is called ignition lag or flame development stage or preparation stage, right? Some books they will write it as ignition lag stage. In some authors they write as flame development stage. Some authors they will call it as preparation stage, right? So I have written all the 3. So the very first stage of combustion is called ignition lag stage or flame development stage. Okay. Then comes the flame propagation stage, right? So this is developing here. Flame is getting developed in the first stage. Second stage, we will be having the complete combustion because of the propagation of the flame into the air fuel mixture, right? So this stage we call it as stage 2. Only during stage 2 you will have the sudden rise in pressure, right? And because of this only the amount of energy released is also going to be higher, and the useful work output we are going to get only from the stage 2. Useful work output for making the piston to move down from TDC to BDC, that is going to happen only in the stage 2. And the last stage, third stage, is called afterburning stage or flame extinction stage. Inside the engine cylinder, the combustion is going to stop, right? So that we call it as afterburning stage or flame extinction stage. So there are 3 stages. One is ignition lag, other one is flame propagation, and the last stage is called afterburning stage, right? And remember, all these 3 stages we are going to represent as soon as we introduce the spark inside the engine cylinder, right? After compression stroke, spark is introduced. From there we are going to consider, right? So these three stages we are going to represent again in the P theta diagram, right? So the P theta diagram, here we are not going to consider the beginning of compression, from the end of compression only we are going to consider, right? In the actual case, we are going to consider from as soon as we introduce the spark. Okay. So coming to the P theta diagram under actual condition, listen very carefully. Okay, listen carefully. So now this is the variation of pressure inside the engine cylinder with respect to the crank angle turn, right? So we are here in the case of actual condition of the spark combustion in the spark ignition engine, we are going to consider only from the moment you are going to introduce the spark inside the combustion chamber, right? So now this point, right? So this is from, let us say in the previous theoretical case, we have started with the compression stroke. So this is the compression stroke, and this is the maximum pressure reached because of the compression stroke, right? Point B is the maximum pressure that is reached because of the compression stroke. But remember, in real case, what will happen? In theoretical, we will say like as soon as the piston reaches the TDC, we will say like a spark is introduced. But in reality, that is not there. We will introduce the spark little bit early. Okay. So before the piston reaches the TDC, spark is introduced. Okay. So this is something out here in this P theta diagram. They represent that 20 degree before TDC. 20 degree before TDC, spark is introduced. I'll come to this the angle turned later. As of now, you consider that this is the place where the spark is introduced. Before the piston reaches the TDC, spark is introduced. So spark is introduced earlier, right? Here spark is introduced. This is the crank angle turn at which the flame starts. See, this is spark introduced by the spark plug. This is the combustion of the fuel starts only here, right? So there is a lag. This they call it as ignition lag. There is a delay in for the combustion to take place. So this we call it as ignition delay or ignition lag. So that is why this first stage of the combustion we call it as ignition lag stage or flame development stage, right? Or preparation stage. This AB. This AB is called stage 1. Here it is written stage 1, right? So A to B is the your flame development stage or ignition lag stage or preparation stage. Okay. So here the combustion starts. From here combustion starts. As soon as the combustion starts, there is a sudden rise in pressure, right? Here you can see there is a sudden rise in pressure. How long this takes place? The sudden rise in pressure. The piston has crossed the TDC now. After the TDC, the piston has crossed the TDC. So this is your TDC position. Before the piston reaches TDC, here we have introduced the spark. Before the piston reaches the TDC, combustion has started, and there is a sudden rise in pressure, and the peak pressure was reached when the after TDC. Peak pressure was reached when the angle turned is after TDC. So this B to C, this is what is very, very important. This is the second stage of the combustion process, and this is the place where we are going to get huge amount of heat release. There is a sudden rise in pressure, thereby we are going to get the useful power output. The useful power output is only from this stage, that is from B to C, stage 2. Now the piston has crossed TDC. Piston has crossed TDC. Now there will be some leftover fuel will be there. There will be some amount of leftover fuel will be there. That will undergo burning, right? The leftover fuel will start to burn during this C2D. But remember, the piston has crossed the TDC. So now the volume available inside the engine cylinder is going to be higher. So whatever the combustion reaction that is taking place and the energy that is being released, that is not useful, right? Because there is no rise in pressure. There is no rate of rise in pressure, right? So this we call it as after burning, right? So there are 3 stages. This is your flame development or preparation stage or ignition lag stage. So this we call it as flame propagation stage, where we are going to get the useful work output, right? And this is after burning stage. Okay. So now let us say you are having some amount of fuel you have injected, right, in the intake manifold, and the air fuel mixture is there. Now it is going to undergo combustion. Here we have introduced the spark. This is the place where the actual combustion starts, right? The flame front is going to be formed, right? Or flame kernel we call. Flame kernel is going to be formed. So during this time, almost something like 5% of the fuel will be burned. So 5% of the mass of the fuel will be burned during this period from A to B. Then almost 80%, 80 to 85% of the fuel is going to be burned during B to C, second stage. And the remaining fuel is going to be burned in the third stage. Now let us say this is 5 to 10%. This is almost 80%. So 90% of the mass of the fuel that is injected is burned. So remaining 5 to 10%, whatever balance that is there, that is going to undergo combustion in the last stage. So during this stage of combustion, that energy is not useful for us, right? So you will not get the useful power output when the after burning is going to happen. That is the third stage of combustion. Okay. So now let us start here. So here, this is the point A where the spark is introduced. The spark is going to be introduced something between before TDC almost 30 degree to 10 degree. That's right. 10 degree to 30 degree in that range, the spark is going to be introduced. Here in the diagram, we have mentioned at a 20 degree C before crank angle. 20 degree before the TDC is represented here. Okay. So at point B, the actual ignition starts, flame front is formed, and this is the point at which you can see the sudden surge in pressure, right? So the engine, the cylinder pressure is the maximum cylinder pressure rise you can observe only from point B, right? From here you can observe. And remember, this increase in pressure starts before TDC. Here in this diagram it is represented 8 degrees C before TDC, right? And there is one more curve is represented here. If you watch carefully, this is written as motoring curve. Motoring curve is nothing but, now let us say you have an engine cylinder and the spark plug is switched off. I'm not going to operate the spark plug. So suction takes place, air fuel mixture enters, and the compression stroke starts. When the compression stroke starts, whatever air fuel mixture that is present inside the engine cylinder, that is going to undergo compression process, and the pressure is going to reach a value which is at point B, right? Now the spark is not introduced. Remember, spark is not introduced. If you don't introduce the spark, then this is the maximum pressure that is reached inside the engine cylinder, right? At TDC, you'll have the maximum pressure. After this, only if a spark is not introduced, then whatever the air fuel mixture that is present inside the engine cylinder, that is going to undergo expansion. When it is going to undergo expansion, then the pressure is going to decrease, right? So this curve, we call it as motoring curve. Without introducing spark plug, if you are going to operate the engine cylinder, right? Now, normally this we used to do, let us say if you are going to have a diesel power plant, okay, or a huge engine is there, right? In the case of a diesel power plant or in the case of a marine diesel engine, before you start the engine, right, before you crank the engine, what we used to do, we used to start the lube oil pump, we used to start the cooling water pump, then we used to have a starter motor. We used to have a motor called starter motor. That motor will start. The engine is not going to run. That motor will drive the engine. We'll start the starter motor. That motor will drive the engine. That means what? The piston is going to move up and down. So 1 or 2 cycles we will be doing like this. In the meantime, lube oil pump is started. Cooling water pump is started. So this will provide the better lubrication. As before cranking the engine, if the engine is a huge engine, what we used to do, we start the starting motor. Once you start the starting motor, before starting the starting motor, lube oil pump is started, cooling water pump is started. Now this will ensure the lube oil movement everywhere inside the engine cylinder, between the piston and cylinder. Then after doing some 2-3 cycles, then we'll start the starting motor. Then we'll go for cranking the engine. Okay. So if the engine is running, when the engine is cranked, then this is the combustion, the P theta diagram for the combustion process inside the engine cylinder. Without the spark plug, right? If it is a diesel engine, without fuel injection, only the air, if you are going to compress and allow it to expand, then that curve is called motoring curve, because here only the starting motor is operating. Starting motor is driving the engine cylinder. Okay, so that is represented by this. So this point B represents the maximum pressure in the motoring curve. Okay, so point B, this indicates the during your actual combustion process, the P theta diagram, if you see, the P theta diagram for the motoring curve and the actual combustion curve, both are following the same trend up to B. Beyond point B, there is a deviation. Motoring curve is following this, whereas the actual curve is having a sudden rise in pressure. So the deviation of the P theta diagram, right, between the motoring curve and the actual combustion curve, that deviation starts only from point B. Okay, so this is point B. The maximum peak pressure reached is indicated by point C. Okay, and the point D represents this is the place where the flame gets extincted, right? So this is the point where the flame that is present inside the combustion chamber that is going to extinguish or extincted. Okay, this is end of combustion. This is point B. So the point A, point B, point C, point D. Point A, in the case of your actual combustion process, this is the place where the spark is introduced. Point B is the place where the sudden rise in pressure is observed, and this is the peak pressure. This is the end of combustion or the extinction of the flame. And AB, BC, CD is there. AB is the stage 1 of combustion, BC is the stage 2 of combustion, CD is the stage 3 of combustion. So this is ignition delay or ignition lag stage. This is the flame propagation stage. This is the after burning stage, right? Is that clear? Yes. Are you there?
Yes, sir.
So is the P theta diagram clear? Actual condition?
Yes, sir.
Okay. See the angle which I have represented earlier in the theoretical P theta diagram, we have represented like this: 180, 360, 540. Correct. Whereas here, see how they have represented. This is 0. They have represented the values are increasing beyond 0. This is TDC, right? So TDC is the reference where the crank angle is represented as 0. This is after TDC. This is before TDC. Okay. So this is 8 degrees C before TDC, 20 degree before TDC, 40 degree before TDC. This is 20 degree after TDC, 40 degree after TDC, 60 degree after TDC. So the 360 degree is nothing but end of first revolution, which is 0 degree for the second revolution, right? And this 540 is your 180 degree for the second revolution. So this 180 is minus 180. This way, if you go, if we are going to keep this as the reference, this is 0, TDC is 0, this is before TDC, this is after TDC. So this is TDC, this is VDC, this is BDC. So if you move this side, then this is before TDC. If you move this way, then this is after TDC. So this before TDC and after TDC are represented like this. TDC will be in capital, whereas B will be represented in small letter. If it is after TDC, TDC will be in capital and A will be in small letter. Okay, so this we call it as after TDC. So if you move towards this side, this is called before TDC. Okay. So in the most of the books, if you see, they will not represent like 180, 360, 540. They will be representing like this: 0. Then positive values will be here, negative values will be here. So before TDC and after TDC. Right. So the actual combustion process, right? So for better clarity, I have made I have zoomed the P theta diagram, actual condition. So A is the spark introduction, B is the ignition start, C is the peak pressure, D is the extinction of flame. A to B is stage 1, B to C is stage 2, C to D is stage 3. Right. So that is what is represented here. Right. So A to B is the stage 1. So this is the flame development stage or preparatory stage, right, where the flame front or the flame kernel is established. Okay, this is what we call as flame kernel or flame front. And this stage, the establishment of the flame front, right, that is controlled by the chemical kinetics of the fuel, which depends upon the temperature of the air fuel mixture, pressure of the air fuel mixture, and the type of the fuel that we are going to use, right? So this AB variation. So it depends upon the temperature of the air fuel mixture, pressure of the air fuel mixture, and the type of the fuel that we are going to use. And coming to the BC, second stage of combustion, here you will find when the ignition starts, right, when the flame is being formed, then what will happen? Initially we will be having the flame has to move, right, within the air fuel mixture. When it moves, initially it will be moving in the laminar condition, then subsequently we will be having the turbulent condition. So during that laminar condition, what will happen? The velocity of the flame is going to be constant, right? The flame velocity, the rate at which the flame is going to travel, that flame velocity is going to be constant, and the propagation of the flame is controlled by the turbulence that is there inside your engine cylinder, right? Okay, so the large pressure rise, as here you will find the very large pressure rise. If you see this is the pressure here at point B, this is the pressure at point C. So this large pressure rise you will experience only during the second stage, right, in stage BC. Okay, And the last stage is what we call it as the after burning stage, C2D. So this is also called as flame extinction stage or after burning stage. So here during this stage only the almost 90% of the air fuel mixture present inside the combustion chamber will be completely undergone combustion, and the flame has reached to the cylinder walls. It has reached the cylinder walls. After the cylinder wall, we are going to have the cooling water circulation, right, in the cooling water jacket. So there will be cooling water circulating. So as soon as the flame front moves towards and reaches the piston, your cylinder wall, so the cooling water is being circulated. So there will be a loss of heat to the surrounding, to the cooling water will be there. So since the combustion products are losing the heat, the flame will get extincted. Okay. Once it reaches the walls, it loses the heat, and the flame gets extincted, and the pressure falls suddenly, and because the piston has crossed the TDC, whatever combustion that is going to take place, that is not going to be useful, right? As soon as the piston moves away from the TDC. Okay, so that is what is represented there. Okay, so all these three stages, right? Let us see in detail again, right? So in the case of ignition lag stage, first stage of the combustion, right? This is the definition for ignition lag is, it is given like this. It is the time period between the spark is being introduced and the first flame, the fuel begins to burn. That time difference we call it as the ignition lag, right? So this stage is also called as preparation stage. So here you can see piston is at the TDC, okay, and the spark is introduced. Here combustion starts, right? The time period between these two, as soon as the spark is introduced and the combustion starts, or the flame front has been formed. So this we call it as the ignition lag. Okay. So now there are two things we have to be very careful. The timing of the spark introduction, that is very, very important, right? Otherwise we will have two problems. The first case is that now before the piston reaches TDC, if the spark is introduced, what will happen, right? We have told that we will be introducing before the piston reaches TDC something around 20 degrees C, right? Now let us say 40 degrees C before the piston reaches the TDC, or before TDC 40 degrees C if the spark is introduced. That means earlier ignition takes place, correct? If the ignition takes place early, then what will happen? Piston is only at the somewhere in between the BDC to TDC. It has come, let us say something around, it is from the TDC, it is before TDC some 40 degree or 50 degree. The spark is introduced. Now what will happen? The combustion starts, pressure inside this will be very high. So the piston will face a lot of resistance to move up. It has to go up now to the TDC, but it will not move up because the pressure is very high. So since the pressure is very high, what will happen? This will push the piston down. So you will have the rotation of the crankshaft in the opposite direction. Reverse rotation will occur if the ignition is early. If the ignition is early, then the engine will rotate in the opposite direction, right? Which is not favorable, which should not happen, right? So the timing of the ignition is very, very important. If the ignition is too early, then engine will rotate in the opposite direction, which is not useful. So the products of combustion is going to push down the piston before it reaches the TDC. Before it reaches the TDC, it will push down the piston. Okay. Now, if the ignition is late, that means what? After the piston crosses TDC, spark is introduced. Now, what will happen? Piston is moving away from TDC. Volume is available is going to be more. So the expansion takes place, but that is not going to be useful. You will lose lot of brake power, right? A lot of power will be lost if the ignition is delayed. Okay, there will be loss of pressure and thereby the power is going to be lost. Okay, so the ignition lag, right? Depending upon the ignition lag only, we will fix the time of spark introduction. Okay, so this ignition lag, it depends upon the type of the fuel that we are going to use, what is the pressure inside the combustion chamber, and what is the temperature inside the combustion chamber before introducing the spark, right? These are the parameters which are responsible, right? So if you want to extract maximum power from the engine, then what is responsible? The important parameter is your brake mean effective pressure. Mean effective pressure is a very, very important parameter. Only because of the pressure inside the your engine cylinder, we are going to get the maximum power output. Okay, so this pressure depends upon proper combustion, right? So if you want to have maximum brake power, we should have higher mean effective pressure, and this is achieved if the ignition starts at the proper timing, right? When the piston is closer to the TDC. That means something around 20 degrees C before TDC is the ideal period. Okay. So timing of spark is very vital. It should be ensured by considering the ignition lag, right? The time required for the starting of the combustion. That is very important. Based on that, this spark is introduced into the combustion chamber for complete combustion and to extract maximum power output from the engine. Okay. Now coming to the second stage, flame development or ignition lag, right? This is the, among the three stages, this is the second stage is very, very important, where we are going to get the maximum power output. Okay. This flame development occurs from here I have written 30 degree. Normally we say like 20 degree. Okay. Before TDC, from that to the before 8 degrees C of the TDC. In the diagram there, initially which we have discussed, 8 degrees C, right? From 20 to 8 degrees C before TDC, this first stage of combustion takes place. Okay. Now, so why we are introducing the spark before TDC, slightly before TDC, that is 20 degree to that 8 degrees C, is that if you are going to advance the ignition, right? Before TDC, if you want to start the ignition, then it is from the experience, it is found that you will get better fuel economy and you will get the maximum power. Okay. Yeah. Okay. So when the flame is formed, right, after introducing the spark, when the flame is formed, the flame front will be spherical in shape, and during this your flame development stage, right, that very first stage of the combustion, the amount of heat released is going to be very small, and the flame radius is something around 5 mm, and among the total amount of energy that is being released by the combustion, only 5 to 10% will be there during the first stage of the combustion process, right? And the time duration of the flame development, right? So that depends upon the temperature of the charged air fuel mixture and pressure of the air fuel mixture and the composition of the air fuel mixture and the flame propagation velocity. Okay. So if the mixture is rich, right? This we call it as equivalence ratio. Phi is nothing but equivalence ratio. This is your fuel air ratio divided by fuel air ratio of the stoichiometry. If the value is more than 1, then it is rich mixture. Correct. This value is more than 1, then it is rich mixture. So if you are going to have a rich mixture, then the flame development is minimum, but the combustion rate will be faster. Right. The development it will take slowly, and whereas the combustion takes place faster. If the mixture is lean, right, combustion will be slow. For lean mixture, combustion will be slow. For rich mixture, combustion will be fast. Okay. Coming to the second stage of flame propagation, right? So this is considered as the most important stage, from where we are going to get the maximum power output. Okay. So during this stage only the flame will start and it will propagate into the air fuel mixture. Now this is the introduction of from the spark plug. So this is your air fuel mixture. Correct. This is the air fuel mixture which is present inside the engine cylinder, and this is the spark that is being introduced. Now the ignition starts. As the ignition starts, this is the flame front which is going to move. Okay, this is the flame. It is going to move towards the air fuel mixture, right? So flame propagates. During this time, the flame propagates at a constant velocity, almost at constant velocity, and the heat transfer is going to be. See, this is the flame front which is propagating. This is surrounded by the air fuel mixture. These are unburnt, whereas here the products of combustion is going to be present. So this is this line which separates the products of combustion and the unburnt fuel, unburnt air fuel mixture. So this we call it as a flame front. Flame front is nothing but which is going to separate the products of combustion and the unburnt air fuel mixture. Okay. So this moves at constant velocity, and see now let us say this is the assume that this is the engine cylinder. Okay. So the flame has not reached the cylinder wall. Okay. So heat transfer, now the combustion is taking place and the heat transfer is not sufficient enough and the heat has not reached the cylinder wall. during the second stage. So this is further propagation of flame into the air fuel mixture. Okay. So the rate of heat transfer depends upon the rate of heat transfer inside the combustion chamber. This depends upon the intensity of turbulence and the mixture of the air and fuel. Okay, depending upon it can be lean mixture, it can be a rich mixture. Depending upon the mixture of the fuel, the rate of heat transfer depends upon the mixture of air fuel as well as the turbulence that is there inside the combustion chamber. Right. So the rate of pressure rise is directly proportional to the rate of heat release. Right, the higher the rate of heat release, the higher the rate of pressure rise. Okay, and the volume of the combustion chamber is almost maintained constant because the piston is at the TDC. Okay, and the volume available is only the clearance volume, so pressure is going to be very high, tremendous. Right, so that sudden rise in pressure is useful for pushing the piston to move down. Okay, so these are all our after burning stage. So in the next slide, I'll explain you about the after burning stage. Okay. So in the case of second stage of combustion, that is flame propagation stage. So we are going to have the fully developed flame, and this occurs till the maximum pressure is reached. That is the point C. Okay, A is the spark introduction. Point B is the place where the ignition starts. Point C is the maximum pressure that is reached. Okay. So during this second stage of combustion, almost 90% of the fuel will be burned in total, right? Almost 10%, 5 to 10% during the first stage, fuel will be burned, and remaining 80% is burned during the flame propagation stage. That means total 90% burn. So remaining 5 to 10% will be there for the after burning stage. So the duration depends upon the flame velocity. The flame propagation duration depends upon the flame speed, and if the products of combustion from the previous cycle of operation that is still existing inside the engine cylinder, that we call as residual gas, presence of residual gas. So depending upon the amount of residual gas that is present, if the residual gas quantity is going to be more, then the flame propagation duration is going to increase. It takes more time, right, to complete the complete combustion, right? So these days we are to reduce the emission, we are using the exhaust gas recirculation. In the exhaust gas recirculation, the products of combustion is going to be again brought back into the engine cylinder, right? So if the products of combustion are going to be present, then what will happen? The flame propagation time is going to be higher, right? So the combustion duration is going to increase because the air fuel mixture is diluted by the products of combustion, right? Now, hello, are you there? Yes.
Yes, sir.
Okay. In another 5 minutes, I'll complete. Okay. So this is about your flame propagation stage, and the last stage is the after burning stage. So these two diagram, right? So almost the 90% of the fuel mass of the fuel is being burnt, and only the 5 to 10% is going to undergo combustion in the after burning stage. Okay. So remember that not the completely all fuel will get burnt during the flame propagation stage. So there will be some fuel left over, right? That leftover fuel is going to burn during the after burning stage, right? So the rate of combustion decreases due to the reduced flame speed and the reduced flame front surface. So in the last stage, after burning stage, so the flame speed is less, and the flame front is also, surface area of the flame front is also less. Okay. So and finally the flame reaches the cylinder wall and it loses the heat, and finally the flame gets extincted. Okay. So remember, at the first stage, 10%, maximum of 10% of the fuel is going to be burned. In the second stage, 80% of the fuel will be burned, and during the last stage, almost 10% of the fuel is going to be burnt. Okay. So if you see here, this is the flame front. This is what we are calling it as the flame front. Okay. So here the flame front is not intersected by any object of the engine cylinder, right? So this is hemispherical we have represented. So it will be spherical in shape, and later subsequently when the flame front propagates, it is going to reach the piston top, right? The crown of the piston is going to be reached, that is intercepted by the piston top. Then finally, as the flame front propagates further, it is going to reach the cylinder wall, and thereby this is the place where it is going to get extincted because it is going to lose the heat to the engine cooling water, which is flowing through the cooling water jacket. Okay. So this flame front is also called as flame kernel, right? So this the extinction of the flame is also called as flame quenching. Okay. So with this we'll stop for today's lecture.